We have found a new particle never seen before in Mother Nature.
We have discovered a brand new particle that has never been observed in Mother Nature. Mio Kaku, a famous scientist, has warned that something weird is occurring at CERN. The most potent device ever constructed, the Large Hadron Collider, was abruptly shut down, and rumors of horrifying repercussions are circulating. The public and scientists are on edge due to theories of reality-altering experiments gone bad and inexplicable energy swings. Is a cataclysmic catastrophe about to begin? Or is the narrative more complex than it first appears? To find out the terrifying reality, stay tuned. Overview of the LHC, or Large Hadron Collider. The European Organization for Nuclear Research, or CERN, is in charge of the Large Hadron Collider, or LHC, a gigantic circular particle accelerator. It measures 27 kilometers in circumference and is concealed beneath the Swiss landscape close to Geneva. It is so vast that a person could walk around its whole ring for over 6 hours. The LHC, which was built between 1998 and 2008, became operational in September 2008 and immediately became a symbol of the highest level of contemporary experimental physics. The goal of testing basic hypotheses about matter, energy, and the cosmos itself is at the core of this machine. The goal of the LHC is to explore previously unimaginable regions, as noted by physicists like Michio Kaku and others. The collider, which is made to smash protons together at extremely high speeds, raises the particle's energy to tera-electron volts, or TeV, which simulates the circumstances only a moment after the Big Bang. Numerous important problems regarding the formation of the universe and the role of quarks, leptons, and bosons, tiny building blocks, in the Standard Model were still unresolved before to the LHC. Scientists anticipated that the LHC will validate established ideas about the origins of mass and reveal novel phenomena, such as exotic particles or forces. The Higgs boson finding, which was announced in July 2012 and confirmed decades of theoretical study regarding a universal field that embusses some particles with mass, was one of the major turning points. The LHC has captivated public interest beyond the realm of pure physics. Some people worry about black holes or speculate about possible apocalypse scenarios, particularly since the collider's early design phases raised worries in a number of media publications. The LHC's sophisticated capabilities make it a lightning rod for speculations about cosmic disasters or the end of reality, despite the fact that leading physicists often brush off apocalyptic worries. Its construction is grounded on practical principles, notwithstanding the fanfare. Putting the equipment underground lowers noise, keeps everything stable, and provides natural radiation protection. Specialized structures above ground house supporting machinery, such as magnets, radio frequency cavities, and cryogenics. Liquid helium guiding beams surround the ring of hundreds of superconducting magnets that cool to almost absolute zero below Earth. Tens of thousands of physicists, engineers, and students collaborate on this global initiative to sort through mounds of collision data using advanced technologies. About 15 petabytes of data are processed annually by the LHC's intricate infrastructure, which then broadcasts the results all over the world. Many people view the LHC as a representation of humanity's search for ultimate truths and its effort to reveal previously concealed cosmic levels. Experiments at each collider ring crossing point yield a number of discoveries that deepen our understanding of the interactions between basic forces. As the machine keeps running, researchers advance in this era of high-energy physics research by improving their models of the cosmos, the composition and operation of the LHC. Fundamentally, the LHC is a combination of two accelerators. It pushes two hadron beams, typically protons, but occasionally heavier ions, in opposing directions around a 27-kilometer circle. Numerous particle events take place when these beams clash after crossing pathways at specific interaction sites. Sophisticated detectors measure the characteristics of tiny subatomic components that spew out in all directions. The time and effort required to shape, direct, and crush the beams in order to optimize the collision rate is a crucial aspect. Strong magnetic fields produced by superconducting magnets, cooled to minus 271 degrees Celsius by superfluid helium, maintain each beam on a circular path. The first injection, which gradually increases beam energy, frequently originates from tiny pre-accelerators. The particles whirl around the loop hundreds of thousands of times per second once they are within the main ring, approaching the speed of light. Early in 2010, the beam energy was 3.5 tera-electron-volts per proton. With modifications, it increased to 6.5 tera-electron-volts each beam. This advancement made it possible to create and detect events that accelerators do to see Higgs. Smaller collider could not produce, almost quadrupling the world's prior records. The ring itself is subterranean, reaching depths of around 50 to 175 meters and winding along a carefully designed path beneath the Swiss-French border. In these crashes, timing is crucial. The intersection of the two beams occurs only at 4 critical locations. Massive detectors known as ATLAS, CMS, ALICE, and LHCb border these locations. Each has a distinct area of expertise. Broad-spectrum physics is handled by ATLAS and CMS, which search for anything from the Higgs boson to speculative supersymmetric particles. LHCb addresses the nuances of matter-antimatter asymmetry, whereas ALICE explores situations duplicated by heavy ion collisions. Although proton-proton collisions are common, the LHC also produces quark-gluon plasma through heavy ion runs, which mimics the harsh circumstances of the early cosmos. A flurry of transient states and subparticles may appear each time the particles collide. Specialized detectors must pass and record these transient signals in real time because many barely last picoseconds before dying. Although the 4 detectors mentioned above are the biggest, the LHC has 7 detectors in total dispersed across the ring. A portion of the collisions that take place are sent to these experiments, which record information on energy, momentum, charge, and decay products. Given the high collision frequency, sophisticated trigger systems are needed for the analysis of collision events in order to determine which occurrences are worthwhile preserving. Costs and construction. The Giant Electron-Positron Collider, which was built between 1983 and 1988, used the vast tunnel that the LHC now occupies. CERN decided to repurpose the tunnel for their new proton-smashing machine when LEP was deactivated in the early 2000s. Although this reuse contributed to cost savings, an aggregate cost of around 7.5 billion euros was still incurred. The project was formally approved in 1995, with 2.6 billion euros allotted, plus a sizable additional sum for the actual tests. It was difficult to make the LHC operating despite intensive preparation. It turned on for the first time on September 10, 2008. However, a magnet quench incident that occurred within a few days resulted in helium leakage and permanent damage, which put a 14-month halt to work. More than half of the superconducting magnets needed to be replaced or repaired. New safety precautions and enhanced protections have to be incorporated into the complex cooling system. This significant setback highlighted the engineering challenges associated with running massive cryogenic systems and sustaining steady beams for prolonged periods of time. However, in 2010, the machine was fixed and reactivated. An all-time record was set at that point when impact energy hit 3.5 tera-electron-volts per beam. Additional shutdowns throughout time allowed engineers to upgrade cryostats, install brand-new superconducting magnets, and improve other gear. With the declared objective of raising beam energy to around 6.88 tera-electron-volts or somewhat higher per beam, the LHC was prepared to push the limit once more by April 2022. Both European countries and observer governments from across the world have contributed to the funding of these improvements and operating stages. This machine is used for advanced research by more than 10,000 scientists from more than 100 nations, guaranteeing a shared intellectual and financial commitment. An established network of computer centers is necessary to distribute the 15 petabytes of data created annually around the world. Because of its level of activity, the LHC has become a focal point for advancements in science and technology. The price also includes insignificant but important things like keeping the beam pipe vacuumed. Sensitive equipment or beam quality can be harmed by even the smallest pollution. As a result, the whole ring is meticulously sealed using cutting-edge vacuum pumps and tight seals that cover every tunnel segment. These engineering decisions highlight why the LHC's construction and operation cost billions of dollars, but they also made possible a variety of experiments that have revolutionized fundamental physics, important discoveries, and accomplishments. The LHC operates in discrete time intervals, or runs, that span a few years each. The first run, which lasted from around 2010 to 2013, produced some shocking findings. The revelation of the Higgs boson discovery, which is regarded as one of the greatest scientific triumphs of the 21st century, on July 4, 2012, topped the list. The standard model framework that has governed particle physics for decades was essentially confirmed when researchers at the ATLAS and CMS detectors discovered signals that matched expectations for the Higgs boson. In addition to the finding of the Higgs boson, Run 1 produced a quark-gluon plasma in heavy ion collisions with lead nuclei. Because this plasma is believed to replicate the universe's circumstances just a few seconds after the Big Bang, scientists may see how quarks and gluons interact at incredibly high temperatures and densities. Other significant observations made during this period were investigations into certain botonium states, which helped to clarify parts of QCD, the theory of the strong force, and quantum chromodynamics. Run 2, which took place between 2015 and 2018, allowed for even more thorough investigations because of the increased collision energies of up to 6.5 TeV per beam. During this time, researchers discovered an astounding number of new hadrons, investigated potential signs that would point to physics beyond the standard model, and deepened their understanding of Higgs boson decay modes. Understanding of the strong interaction was further refined by the cooperative efforts of experiments at the LHC, which by 2021 had discovered about 59 new hadrons, many of which were exotic states like tetraquarks and pentaquarks. After a 3-year hiatus for significant maintenance and improvements, Run 3 got underway in April 2022. For Run 3, plans call for raising the total number of collisions observed and pushing collision energies just beyond 6.5 TeV. These initiatives aim to gather enough information to improve measurements of well-known phenomena and maybe find really uncommon occurrences. The potential to find new physics signals that were too weak to pick up in previous runs is one of the highlights. Another noteworthy, the date of the milestone was July 2, 2022. With the declaration of a new pentaquark that has a blend of quarks and antiquarks, one of which is an odd quark in addition to up and down quarks. By looking at odd pairings such as these, researchers can evaluate the boundaries of ideas explaining the powerful nuclear power. During these runs, the technology of the LHC has proved adaptable, sufficient to support a range of beams. Even if there are still proton-to-proton collisions as the primary event, the device is capable of collisions between heavy ions or even proton ions for specialized research on nuclear issues. Every collection of data shows something fresh, information on particle interactions beneath high concentrations of energy. The combination of 4 significant experiments, CMS, ATLAS, ALICE, and LHCb, has decoded phenomena across the subatomic world. ALICE's heavy ion collisions produced brief quark-gluon plasma droplets. LHCb studies rare decays and examines the imbalance between matter and antimatter. ATLAS and CMS searched for unusual particles that could give insights concerning supersymmetry or dark matter, the boson of Higgs and its importance. Among the landmark accomplishments of the LHC stands the Higgs boson discovery, disclosed to the public on July 4, 2012, to the enthusiasm of physicists everywhere. Late in the 20th century, speculative suggestions from the Higgs field, a prevalent energy field that slows down some particles, endowing them with mass, emerged. Without it, particles would continue to exist massless, and molecules, atoms, and ordinary substance wouldn't form. As soon as the experiments at the LHC revealed a clear peak about 125 GeV Cs, SU2, in line with the forecasts of the Higgs boson, it validated a crucial element of the Standard Model. They comprehended the boson as a Higgs field excitation, such as a ripple in the ocean of the cosmos. This confirmed the hypothesis that the observed particle's mass spectrum originates from their engagements with this domain, not from a last-minute task. Physicists Peter Higgs and Francois Englert were awarded the 2013 Nobel Prize for contributions to the theory behind this discovery. But the tale doesn't stop there. Continuous queries include whether the Higgs field might relate to situations involving hidden dimensions or dark matter. A few even consider fictitious vacuum conditions, where a local energy holds the Higgs minimum that may theoretically deteriorate. Although it is theoretically possible, any cosmic transition from a fictitious vacuum to a deeper ground state is considered very unlikely on human time scales. Most importantly, Higgs boson's measured attributes continue to correspond with projections using conventional models. However, minute variations may indicate unknown physics. For this reason, the LHC continues to collect further information. Scientists are always searching for irregularities that might point to fresh theoretical directions. Even small changes in diminishing probabilities might indicate sophisticated hypotheses such as supersymmetry, or demonstrate how Higgs couples to heavy particles. Additionally, the Higgs has greater significance for the development of the universe's structure. Not long after the Big Bang, the Higgs field played a role. If matter had acted differently, it may never have merged to form galaxies and atoms. In essence, the reason life exists is because of a cosmic collaboration involving the Higgs mechanism observed firsthand and recorded through boson interactions. Researchers aim to improve their understanding of the universe at its earliest periods and the precarious equilibrium that permits mass-based organisms to flourish. Additionally, the notion of a fake vacuum comes up while discussing the Higgs field. Some physicists argue that the Higgs field may not actually be in a true ground state but a local minimum, stable over cosmological time scales, though theoretically, it could tunnel into a state of lesser energy. If such an event took place, it might change the entire cosmos in a surge of devastation. However, the timeline for such a fictitious event is so lengthy that it surpasses the age of the 13.8 billion-year-old universe and doesn't produce immediate concern. Among the thrilling events of Run 3, a distinct phenomenon on July 7, 2022, caught public focus when a fissure in Earth's magnetic field remained open for 14 hours. The solar wind ionized and streamed in, causing a geomagnetic storm that created breathtaking auroras visible throughout portions of the US and Canada. This coincided with the enhanced run of the LHC. The occurrence stoked speculation that high-energy collisions might have weakened Earth's magnetic shield. But space weather specialists attributed it to co-rotating interaction regions, CERNs, emitted by the Sun. Like coronal mass ejections, CERNs squeeze and disrupt the magnetosphere, sometimes producing temporary vulnerabilities. NASA researchers describe our magnetosphere as leaky, with intermittent windows that allow solar wind entry. The July 2022 crack, open for far longer than usual, emphasizes the dynamic character of solar debris striking Earth's protective barrier. Researchers from organizations like NOAA categorized the resulting geomagnetic event as moderately mild, strong enough to paint the skies without seriously interfering with power or satellite grids. However, the extended opening offered northern viewers prime aurora displays as swirling hues danced across the horizon. The curious alignment with the LHC's busy schedule sparked theories connecting both events. Skeptics pointed to the LHC as a catalyst, linking its high-energy collisions to planetary-scale phenomena. Yet scientists refute such claims, noting that no known collision mechanism underground could produce enormous magnetic rips in Earth's shield. Despite their impressive human engineering scale, the energies at play are small compared to cosmic rays that strike Earth daily. Still, the magnetic field split became fuel for end-of-world theories and LHC-related conspiracies. Due to the storm's visibility and timing, social media discussions exploded. Ultimately, data from solar weather monitors connected the crack to a solar wind stream, demonstrating no connection to the collider. The resulting auroras were simply a beautiful side effect of solar-Earth interactions, not a danger from particle physics. Every time a groundbreaking project like the LHC pushes scientific boundaries, questions about potential risks emerge. One is the idea of a fake vacuum triggered by high-energy collisions. If the Higgs field suddenly dropped to a lower energy state, it could theoretically be catastrophic. But researchers point out that cosmic ray collisions already exceed LHC energy levels. If such events could be easily triggered, they likely would have happened long before humans built colliders. Another concern is micro-black hole formation. In principle, established physics permits quantum gravitational effects at high energies to form tiny black holes. But if they were formed, they would either evaporate immediately via Hawking radiation or be harmless at microscales. Natural cosmic collisions with LHC-level energy already occur in the upper atmosphere, yet no black doomsday holes have emerged. Studies published before LHC construction support this safety, finding no threat from hypothetical black hole production. Conspiracy theories persist. Some claim the LHC opens portals to other dimensions or is a government mind control device. Online myths sometimes connect it to doomsday prophecies, mental manipulation, or unleashing demons. One popular rumor features images of the Hindu statue Shiva at CERN, misinterpreted as a symbol of worshipping dark forces. In reality, the statue is a cultural gift from India, symbolizing the cosmic dance of creation and destruction, an apt metaphor for particle physics. Some conspiracies link LHC experiments with strange storms or magnetic anomalies, like the July 2022 incident. Scientists dismiss these ideas as lacking plausible physical mechanisms. Concerns have also arisen about LHC power unleashing unmatched energy on the Higgs field, causing cosmic alterations. Although the Higgs vacuum remains a topic of theoretical debate, the probability of vacuum collapse is infinitesimal, almost zero across billions of years. Cosmic rays routinely collide with Earth at energies beyond the LHC, with no signs of dimensional tearing or catastrophic collapse. Much of the fear is driven by confusion and the complexity of advanced physics. The LHC's jargon and tech can seem intimidating, leading to misunderstanding or oversimplification. CERN addresses these rumors openly, sharing its scientific goals, results, and operations with the world. Public outreach, research papers, and open data initiatives all counter misinformation. The LHC's impact extends beyond pure particle physics. Each technological upgrade fuels advancements in engineering, computing, and medicine. For instance, superconducting magnet tech enhances MRI systems. Data analysis techniques from CERN support climate modeling and industrial simulations. The Higgs boson discovery showcased the power of global scientific cooperation, inspiring similar projects in space and biomedical research. Governments and funding agencies see the LHC as proof that fundamental science drives transformation and innovation. The collider represents contributions from 10,000-plus scientists, technicians, and students worldwide. With more runs ahead, the LHC could uncover new forces, dark matter particles, or clues about gravity. Dark matter accounts for 27% of the universe's mass energy. If the LHC doesn't detect it, future experiments or next-gen colliders may be required. Another research avenue is extra dimensions. Theories like string theory and brain models propose more than 4 dimensions. If these exist just beyond current detection limits, LHC collisions could reveal them through unexplained energy momentum loss. No conclusive proof has yet emerged, but the quest remains compelling. Heavier ion collisions recreate Big Bang conditions, allowing exploration of quark-gluon plasma mere microseconds after the universe began. This helps scientists understand how matter first formed. Beneath all this lies the principle of gradual progress. Each run, 1, 2, 3 gathers data and sharpens accuracy. Run 4, starting in 2029, will likely boost collision frequency by a magnitude, creating datasets capable of revealing subtle effects or new phenomena. The LHC also fuels education. Universities worldwide offer degrees focused on CERN-based particle physics. Graduate students gain hands-on experience in physics, engineering, data science, and large-scale problem-solving, skills transferable to many fields. Thanks for tuning in to another episode. If you're still here, please click on screen for more high-quality video content.